Welcome back. We rested for a few seconds there and we are ready to go on again. We said we are going to do question number 2 and see what is it that we can take from question number 1 and into the exam room. Question number 2 says a learner conducts an experiment, an investigation to determine which combination of the two half cells provide larger EMFs under the standard conditions. And then here we've got the 3 half reactions or half cells that are represented by A, B, C. A is this one where we've got magnesium turning into magnesium ion. B, you've got lead turning into lead ion. And C, you've got aluminum turning into aluminum ion. So the questions are asked here. The learner set up a galvanic cell using different combination of the above half cell. So in one beaker he will use magnesium and lead, the other beaker, and then the next one will use magnesium and aluminum, lead and aluminum, and check which one will give this learner or will provide him with a bigger or larger EMF reading. All right. So the first question says you must write down the standard condition under which this cell operates. So this is the second time we come across this question, and it should just come to you that there are no gases involved, therefore I must talk about 2 things, and because there's 2 marks here, the one is concentration. So we go into it. Question number 2.1. The standard conditions we said is temperature, and the other one is concentration. So it's important you don't just write temperature and concentration, you must indicate how much is the temperature and how much is concentration. Because if you just write temperature and concentration, you're going to lose marks. So indicate to them that temperature should be between 5 degrees Celsius or 298 Kelvin, and the concentration is 1 mole per cubic decimeter. Then you know that you've got your 2 marks. All right. The next question says write down the dependent variable for this investigation. Okay. So how do you see which one is your dependent variable? The answer for this one is number 2.2. Our answer there is half cell A is our answer for this standard condition. The dependent variable. And remember, the dependent variable is you see what is happening here. They've got 3 cells represented by A, B, and C in the table below and are available. So you've got this one which is paired with that one and is also paired with that one. So the dependent variable. Okay. They say H is our dependent variable. The next question, they say use the table of standard electrode potential to determine which one of the 3 half cell A, B, or C contain the stronger reducing agent. Let me just show you. This is the table they are talking about, and I don't know which one you used in class, but the one that you used in class, you should be able to use it. So in class, I use this one, the 4B, with lithium on top. Because if I use this one, I know that at the top, I'll have oxidation, and at the bottom, I'll have reduction. If I choose 2 half reactions, the one that is on top will be oxidation, the one at the bottom will be reduction. So if you use 4A, it works the same way. It's only that on top you'll have reduction, and then at the bottom you'll have oxidation. Okay, so this one will reverse the half reaction, and that one will write it as it is. And then the one that I use, which is 4B, the one that is on top, you change it, you reverse the reaction, and the one at the bottom, you write it as it is. Okay, so they say you must use this table to determine between A, B, or C, which one contains the strongest reducing agent. Okay, so let's go into it and see which one contains the strongest reducing agent. So let us try and identify A, the half reaction of A, the half reaction of B, and the half reaction of C. If you go into this table and see, we've got magnesium there, which is one of the half reaction, and according to the table there, magnesium is reaction A, and then reaction B, we've got lead into lead ion, Pb. Let me see, where's Pb? There is Pb turning into Pb solid, and then the last one is aluminium Al. Al. Okay, there. So that is A, this is B, and then that is C. So back to the question, it says which one, use the table of standard reducing potential to determine which one of the three is the strongest reducing agent. Reducing agent is the one that gives electrons easily or easier. Table of ours. We said the one that is on top will be the one that gives electrons easily, because you see the arrow this side, it says increase in reducing ability, meaning that magnesium will lose electrons easier than aluminium and easier than lead. So our answer is A, B, or C is reaction A. This is 2.3.1, and they say the answer is half reaction A. So half reaction A, according to this table, is the one that will lose electrons easy, the strongest reducing agent. Okay? The next question, number 2.3.2, the strongest oxidizing agent. Oxidizing agent, according to our summary, we said it is the one that will gain electrons easier. So the arrow this side says increase in oxidizing ability. In other words, lead will be the one that we are going to choose in this case for the strongest oxidizing agent, 2.3.2, and then from our question, lead is number B, half cell B. The answer is half cell B. All right. And then the next question, number 2.4. Number 2.4 says, without any calculation, write down the combination of the half cells which will produce the high EMF. Write down AB or BC or AC. Okay, so let's check. According to our analysis here, we've realized that A is a stronger reducing agent, and B is a stronger oxidizing agent. In other words, if we go back to our table there, C is not there. C is somewhere in between. You don't know whether it's not the stronger. So A and D, A is the stronger of that one, and then D is the stronger. So if you've got both of them as stronger, it means the combination there for 2.4, which will give us a greater reading of the EMF, will be the combination of AB. The combination of AB, because the question says which one will give us the greater reading for the EMF, AB or BC or AC. You see, these two, they've got C and C, it means they are out. So the answer there is AB. All right? And then the last question for, oh, it's not the last question, 2.5. One group of learners set up a galvanic cell using half cell A and B as shown in the diagram X. In the diagram below, X represents one of the components of the galvanic cell. All right? And then there we've got beaker A and the half reaction that is taking place in beaker A, beaker B and the half reaction that is taking place in there, and then we've got component X. And then the question says the name or the symbol that will act as the anode in this half cell, and then you give the reason for your answer. Okay, so they want the substance that will act as the anode in this half cell. So let's see number 2.5.1. So in this case, because if we look at our table, the electrode potential table, we said the one that gives us the bigger reading is the half reaction of magnesium and lead. So we'll have, before we get to the answer, we've got the oxidation there as Mg. I'm going to reverse it. I'm not going to write it, just it appears there. Mg with the arrow, Mg2 plus 2 electrons. And then with the lead one, it's Pb, that is our reduction. Pb2 plus 2 electrons, which will give us Pb. Now the question says we must write down the in symbol the one that is the anode of the cell. The anode, we said anode, I'll keep on reminding you of this. At the anode, we've got oxidation taking place. Oxidation. All right. So between our two half reactions, this is the one that is oxidation. So the electrode that is responsible will be magnesium. So they say you can write the symbol or the name of the substance that is the anode. So it's either Mg or magnesium in full. And they say you must give the reason for your answer. And the reason is, you know that magnesium is oxidized. It's oxidized because it's the one that loses electrons. It's the reducing agent. It's a stronger reducing agent, therefore it's oxidized. Or you can say it, the oxidation number. Remember there, the oxidation number is 0. It changes from 0 to 2 plus. Therefore, there's an increase in the oxidation number of magnesium. That is why magnesium is the anode. All right. Use the reason that magnesium is oxidized, or you look at the oxidation number, it changes from 0 to 2 plus, meaning that the oxidation number increases if it changes from 0 to 2 plus. Therefore, in that case, magnesium will be your correct answer. Number 2.5.2 says we must calculate the initial EMF of this cell. The initial EMF of this cell. Alright? If you remember in one of the summary we said the equation there is 5.2 E cell is equals to E cathode minus E anode. And remember I said you must write it the same way as it appears on the formula sheet. Don't try and modernize it and do it your own way. Write it the same way as it appears on the formula sheet because those are the marks that you don't want to lose. Alright? Then we go into our table. We check where magnesium is. Remember we start with the cathode, and the cathode is this half reaction here. Red cat is the lead one. We start with lead and then we finish with magnesium. So on the table we check lead says there minus 0.13 and magnesium says minus 2.36. Okay, so those are the values that we are going to put here. Minus 0.13 minus that minus there. It's that minus there. In brackets, magnesium is minus 2.36. Minus 2.36. And then you get your calculator, you press minus 0.13 minus minus, and then that sign will change into plus. Therefore, the answer here will be a positive answer. And then the answer there you will find in the calculator is 2.23. And then you don't forget the unit, volt, 2.23. So this is the initial EMF reading of our cell. All right? The next question says, my questions are moving away from me. Number 2.5.3. How will the increase in the concentration of the electrolyte of the half reaction B affect the initial EMF of the cell? Write down increase, decrease, or stay the same. You remember this type of question we came across when we were doing question number 1. I can't seem to find it. Okay, here it is. When we were doing number 1.6. How will an increase in the concentration of silver ion influence the current? And then this question is repeating itself. Briefly, how will the increase in the concentration of the electrolyte of the half cell B affect the initial EMF? And the answer we said will be the same as that answer that we got before. 2.5.3, which is increase. And then if they ask for the reason, you give the same reason as what we gave there. That when you increase this, the rate of the forward reaction increases, and then the electrons released per unit time also increases. There will be more electrons produced per unit time. But then this one, they don't need a reason. They just want you to indicate whether the increase in concentration of one of the electrolyte, which is half cell B, when you increase the concentration of that electrolyte, how will it affect the initial reading of the EMF? Okay. The last question, 2.5.4, briefly explain how component X ensures neutrality while the cell is functioning. Okay, so this symbol X is this one, which is a salt bridge. So the question is, how does it ensure neutrality while the cell is functioning? Okay, so what it does is it allows, remember here you've got electrons that are moving from this side to the cathode side, meaning that this side will have more because you've got electrons coming to this side, and then this side you end up having more positive. So what this soil bridge does, it helps with the migration of the ions. So if it finds that this side is more negative, the positive will go to this side so that it neutralizes the negative that is this side. And then if this side is more positive, the negative will move to this side so that it neutralizes the positive that are on the anode side. So it allows the migration of the positive ion to the cathode electrode. I mean the cathode half cell. So this is the cathode half cell where the electrons are moving into. So the soil bridge makes sure that the cation, which are the positive ions, to migrate from the anode side of the half cell to the cathode side of, so that the electrons that are received on this side doesn't become more negative. All right. So the soil bridge it makes sure that the positive ion migrates from this side to that side, so that there is neutrality of the half cell there. It doesn't become too much negative. All right. So they say it allows the migration of the ions to the cathode half cell, that is cell where electrons are being received. Okay. So that is question number 2, which comes from 2012 February, March. Now we go to 2013 February, March. So you might ask yourself, why this February, March? It's because it's not most of the time that you come across these questions that are coming from February, March. That's why I want to go through them and you become familiar with them. All right. So this